Welcome to the Explainer. Today, we're going to break down the essential math behind how neural networks actually learn, a process called backpropagation. And you're going to see it's all built on just a few core, really elegant observations.
We talk a lot about networks learning by adjusting their weights during training, but what does that really mean? How does a network know which weights to adjust and by how much? It can feel a little like magic, right? But it's not. It's pure mathematics.
So to really get to the bottom of this, we're going to treat it like we're assembling a puzzle. We're going to put together a few key mathematical pieces that, when you click them together, reveal the exact mechanism behind how a network actually trains itself. So here's our roadmap. We'll start with our blueprint, then we'll assemble our three core mathematical pieces: the loss, the mechanics of a single node, and how they form a chain. And then finally, we'll find the one mathematical key that unlocks the entire process. Okay, let's dive right in. Our goal here isn't to learn brand new concepts from scratch. Nope. It's to take what we already kind of get about how networks train and learn to express it precisely, in the language of mathematics. This translation, that's step one. The very first piece of our puzzle is something called the loss function. The easiest way to think about it is like the network's report card. It's just a single number that tells us exactly how wrong the network's prediction was for any one training example. And mathematically, it looks like this. To get the error or loss for just one output neuron, we take the network's actual output A, we subtract the correct answer, Y, and then we square the whole thing just to make sure the result is positive. This tells us the error for just one specific part of the final answer. Now, what's really powerful here is just how simple this is. Say a network is trying to identify 10 different digits. This formula doesn't care about the overall performance. It just tells us how wrong the network was on, for example, the neuron for the number 7. It's a very focused, specific measure of error. But, of course, we care about the whole answer, not just one part of it. So, to get the total error for the entire network on a single training example, we just add up all those individual errors from every single output neuron. And this is a huge deal. We've now successfully boiled down the network's entire performance on a really complex task, like figuring out a handwritten digit, into one single measurable value, C0. The bigger this number, the worse the network did. And the goal of all of this training is to make this number as small as we possibly can. All right, we've got the loss defined. Let's fit our next puzzle piece into place. Now we're going to zoom in from the whole network down to just a single neuron and define its mechanics in mathematical terms. So we know that a neuron gets signals from the neurons in the layer right before it. This formula, well, it's just a fancy mathematical way of saying exactly that. The total input to our neuron, which we call Z, is just the sum of all those incoming signals, A, where each one is multiplied by the strength of its connection, its weight, W. Now, a neuron doesn't just add up its inputs and pass the sum along. It processes that sum, Z, through something called an activation function, which we're labeling G. And this function is what decides how strongly the neuron should fire and what its final output, A, is actually going to be. Okay, so we've got our pieces laid out: the loss, the input to a neuron, and the output from a neuron. So what happens when we connect them? Well, we're about to see they form a perfect chain of dependencies. And this right here, this is brilliant because it lays out the core logic of the entire system. The final loss, C, is a direct function of the network's final output, A. That output, A, is a function of the input it got, Z. And that input, Z, is a function of the weights, W. See? It's a linked chain, one piece depending on the next. So what this really means is that the final error value isn't just randomly connected to the weights. No way. It's linked all the way back through this mathematical chain. The error is a function of a function of a function of the weights. And in math, we have a name for that. It's a composition of functions. And this one observation, the fact that the loss is a composition of functions, that is the entire reason we built our blueprint. Because it tells us exactly what mathematical tool we need to use to figure out how to train this thing. So let's frame the ultimate question here. Our goal is to see how a tiny change in any one of those weights affects the final loss. That means we need to find the derivative of the loss with respect to that weight. So how do you find the derivative of a chain of functions? If you've taken a calculus class, you're probably yelling the answer right now. It's the chain rule.
This single tool is what makes all of backpropagation possible.
The chain rule is the mathematical master key. It allows us to efficiently calculate the exact impact of every single weight in the entire network on that final error. It gives us the gradient, which is just a signpost telling us which direction to nudge each weight to reduce our overall loss. And that process, that is learning, expressed as an algorithm.
So, we've assembled all the puzzle pieces, and we've found the key that connects them all. Understanding this chain of functions is the absolute foundation for grasping how backpropagation actually works under the hood. So the next logical step is to turn this key and unlock the calculations.